Today we're gonna talk about how to model clouds and cloud microphysics. Um, this is very extensive subject, and of course there is no hope to cover all aspects of it in one lecture. So I will just give you several kind of ideas on how to approach this problem in general. So clouds are very important for the climate system. Of course, you know that. First of all, they produce precipitation, and that's very important to sustain life on at least on the land. On the other hand, they are very important for radiative transfer in atmosphere. So clouds can reflect sunlight, thus cooling effectively the climate system. At the same time, they actually enhance greenhouse effect by providing this blanket that prevents infrared radiation from escaping directly to space from the surface. And overall effect of cloud though is cooling. So cooling, or this kind of albedo effect, a reflection of sunlight, actually is a stronger effect overall than greenhouse effect, additional greenhouse effect provided by clouds. So clouds are very important to maintain temperature within a livable range on this planet. So we need to model them somehow, and one of the biggest problems with cloud modeling is that they are relatively small. So I'm not talking about those large, big frontal systems that you can see from satellites that can span space of hundreds of miles, even more. I'm talking about like individual thunderstorms, convection in tropics, maybe besides tropical cyclones, so that could be also pretty big. But generally, even in those systems, individual elements of those systems are just individual clouds merged in some groups of clouds in this kind of aggregated state. But each of those elements or individual cloud cells, they live by their own kind of set of rules. And we need to somehow model them as realistically as possible. And that's the problem because a typical cloud cell can be just several kilometers in size. So a typical updraft core, that kind of main shaft of air rushing up in clouds, inside the clouds, can be hundreds of meters in width. While our grid sizes in our typical kind of regional models or weather forecasting models is actually, grid spacing is much larger than that. We don't have models yet, weather forecasting models that have say several hundred kilometers over extensive area, not just US territory of United States, but bigger than that. And so we have kind of one of the main difficulties arises from that fact that we cannot actually resolve well enough most of climatologically important clouds. And so we need to make certain assumptions about how clouds, for example, behave on subgrid scale, or maybe they just even not make that assumption and say that one individual grid cell is completely, if it's above saturation, it's completely covered with cloud field, and there is no kind of subgrid variation of cloud field, even though it's very highly unrealistic. But in certain models that already high resolution, say large eddy simulation models, that's pretty plausible assumption, because their resolution is such that they resolve actually individual clouds for most part. Another difficulty with modeling of cloud that even though we know quite well the equations or the physics that drive those clouds, we generally don't have input information for our models to simulate them properly. For example, you well know that clouds condense not just from if you have 100% relative humidity and above, you don't have just condensation into clouds directly. It's well known from cloud physics that you need several 100% relative humidity to actually create cloud droplets as I observed. Yet we know that only slightly higher supersaturation or saturation above 100% relative humidity is required for clouds to appear. And this apparent paradox, of course, as you well know, is resolved by so-called heterogeneous condensation or nucleation that involves some foreign particles, usually soluble particles or some other solid particle that have affinity for water. So those particles help to overcome this barrier to condensation that without them would not be possible. And those particles are called cloud condensation nuclei. And similar process exists for ice phase in clouds, for frozen phase. So we need that information about concentration of those particles if we want to simulate with a high degree of realism those clouds. And we don't have that information usually. At least like imagine a global model, we generally don't know distribution of cloud condensation nuclei everywhere in the atmosphere. We could measure them in certain places, but it's very difficult to extrapolate these results to bigger areas than your measurements made over. So we need to make some compromises, of course. And so I'm not going to talk about those kind of aspects, how you actually deal with all these issues of interaction of aerosol with clouds. This is more physics kind of subject of physics. And we here in numerics class. So basically, here I'm going to mention several ways you can incorporate clouds in your models. So there are two general approaches to cloud modeling. First one, so cloud modeling. So basically there are two approaches. First one is to represent, it's the most comprehensive one, is to represent not only information about total properties, kind of bulk properties of clouds, like amount of liquid water and total concentration of particles, effective size of those particles, and stuff like that, but actually to simulate actual distribution of those particles or droplets or ice crystals by their size. So you basically represent the spectrum of sizes. And that approach is called bin microphysics. And this approach is allows you to really represent all this complexity of processes that occur in clouds. But it comes with a price. This approach is extremely computationally expensive. You can imagine now instead, in addition to your three-dimensional space, x, y, z, you have actually one extra dimension, which is size of particles. So you have now four-dimensional space, and sometimes people even use additional dimension that, for example, also tracking the size of aerosol those individual particles were created on. So now you have five-dimensional space. And if you use, say, typically several hundred grid points in that size space, for example, and then you have several thousand grid points in X, Y, and Z in each direction. There is no generally computer available now to do it, to do any good job using a relatively large domain that incorporates many clouds. So those models still exist, but they usually deal with individual one cloud, idealized cloud, some updraft, some bubble rising, and some processes happening there. But this approach cannot be used in, say, weather forecasting or some models for model domains that are relatively large, that incorporate, say, large cloud systems like squall lines and stuff like that. So this approach is not used for that. So it's more kind of theoretical study. So get some information about process to be used in other approach as some kind of parameterization. So it's basically a similar situation than when you use a large edge simulation model to derive certain relationships for turbulence that then you can use for larger scale models. So it's very expensive. And it's both in terms of CPU computations and also in terms of storage that you require for that. Very expensive. Another approach which is currently very common and used in most of models, in all weather forecasting models, in all climate models, everywhere, is so-called bulk microphysics, bulk. So bulk microphysics. So in this approach, you predict just certain bulk qualities of cloud, such as like properties of cloud, such as, for example, total liquid water content or some mass density of cloud, or total concentration of all particles, so that if you have those two variables, you can get some idea about some mean average size of those particles that can be important both for rain formation and also for radiative properties of clouds. It's known that smaller particles in clouds reflect and scatter sunlight, for example, much better than if you have bigger particles. That's why, like when you have rain, big particles, rainy clouds, they kind of appear dark, and when you have this kind of fair weather, not raining cloud, they appear this bright white. And this is a direct consequence of the fact that in raining clouds, particles are bigger, so they reflect sunlight much less efficiently than clouds that don't have rain, that can consist of small particles. So you can have this other, like total amount of ice, pristine ice, small particles of ice, total amount of snow, for example, characteristic size of snow particles, and then how they fall. And there are numerous approaches to this bulk microphysics, and there are many of them, probably dozens and dozens of them currently being used, and people are very creative in various ways to make the kind of magic very successful cloud microphysics. And unfortunately, there is not a single one which is really, really good. It can be good in one aspect because it was kind of designed for certain type of cloud, and then you use it in a different setting for different clouds, say in tropics, and you designed your scheme for mid-latitude storms. And in tropics, it can produce very unsatisfactory results. So people generally, probably strategy for that is depending on which type of clouds you're actually simulating, you choose best microphysics that can support your observed kind of clouds. For example, if you have some observational constraints on particular event and stuff like that. So like WRF, for example, weather forecasting model, which is a kind of state-of-the-art of cloud modeling for mass users. So now anybody can just download that model, run it, and become cloud modeler without even understanding how it works, unfortunately. That model has literally dozens of, couple dozens at least, of cloud microphysics schemes that you can choose. and which is a good thing. So it's diversity in this case is always good, because there is not a single bold microphysics that can be good for all situations, because clouds are so complex. So let's talk a little bit about, just give you an idea how those two approaches work in general. So bin microphysics. So for bin microphysics, as I mentioned before, you predict PDF, or probability distribution function so it's basically concentration of particles as a function of size. So you predict, say this is your size or mass, for example, which is more appropriate for, say, ice particles, because size is kind of ambiguous quantity of ice particles. They can be flat, they can be like, what's the size of dendrite? We can choose like some outer kind of circle that it incorporates it, but what about thickness of that dendrite? How you incorporate that too? So the easiest one usually people use is mass. And here you have this F. This is your probability, and then you have some spectrum like that. So this for small masses, it can be cloud water, and this kind of secondary peak, it can be rainwater, so the bigger particles. So you have some size distribution, which is a function of radius or mass. And also, of course, it's function of position in space, in three-dimensional space, and also function of time. So this is your goal. You predict this distribution function, and this distribution function is defined such that you can compute, as long as you know it, you can compute concentration of particles. Concentration, like defined as concentration equals this total integral from 0 to infinity of this F over all masses. And just so it's in a way, it's a zero moment of this distribution. And mass, total mass, you compute as total integral from 0 to infinity mass times F dm. So it's a first moment of distribution. Then you can compute, for example, radar reflectivity, so how well cloud reflects radar signal. Radar reflectivity, Z usually, it depends as the size of particles in the power of 6. So it's only very large particles reflect well a radar signal. So in that case, so it's proportional to mass in power of 3. So radar reflectivity can be computed as this integral proportional to integral of mass cube f dm. So it's a third moment of distribution. So as long as you know distribution, you can compute all sort of nice metrics. You can compute mean radius, for example. You can compute mean area, which is important for computed for radiative properties, reflective properties of clouds, because it's kind of area of particles that reflect the sunlight, for example, and so on. So this is a very comprehensive way. You can basically, by predicting one quantity, which is F, you basically predict all properties of clouds. And of course, you can have this F for each of particle sizes. For example, for cloud droplets, it's one distribution, and then, but you cannot mix it with ice particles. So you have another distribution, say, for ice particles which are, say, flat, say some dendrites or say some plates, and then another distribution for particles that consist of columns, and then maybe another distribution that on particles that actually look like these clumpy things like graupel or something, or hail, and then yet another distribution you can have for this kind of aggregated particles that consist of many ice crystals kind of stuck together, which is snow, like snowflakes. these particles of snow. So so this distribution you treat it, so you see it's a function of this many variables. So you know how to deal with x, y, z, and t. It's just transport problem of your particles. So you have just normal, you solve normal equation, say in flux form, or you can solve it in the, let's write it in flux form, say, well, density, let's say 1. So you have this convergence of your fluxes, so first of all, numerically, what you have to do, you replace this distribution by beans. So you divide your mass space into maybe equal or logarithmically spaced kind of beans. That hence the name bean microphysics. And you basically replace your kind of continuous PDF with this kind of histogram PDF with kind of this. So your PDF becomes something like that. So, and you fix those sizes so you don't move them. So you basically have n, like many variables. So for each of those, like fi, so this one becomes fi, where this is index I, 1, 2, 3 beans that count the number of beans. So you write for each of the beans of your distribution, you treat them kind of independently, but they can interact, of course, with each other. So for each of the beans, you just transport them, which is like, say, u. So if you, if it's like, it's, yeah, well, so u f I plus transport in y v f I plus transport in z, and here there is first complication. Well, not complication, but kind of addition. Here you have vertical velocity of air, but also particles fall down. They have sedimentation, they sediment down. So you have some sedimentation velocity here, let's call it like v as a function of mass of this moment I. So you see it's negative because particles fall down, and this terminal velocity of these particles, it depends of course on mass. And now this is, so this is just normal advection, or normal advection equation that we solved. It's just some quantity f. And of course here additional complication is that this f cannot be negative, so you need to use positive definite or monotonic scheme for this quantity f, and that's another complication because those are expensive, so that makes it even more expensive. So, and now you need to add a movement in size space. So each bean actually can move by condensation or by other processes like collisions and stuff. So they can move, well, not by collision, it's actually different, but by condensation itself, like particles of certain size, they basically move in this size space. So this is like x, y, and z. So now you have size or mass space, whereas this your distribution is actually transported the same way it transported through three-dimensional space. It's actually also transported through mass space. So you need to add this term here. So d over d mass, and here d mass dt due to condensation, or in terms of, or evaporation, or in terms of ice, it can be sublimation or deposition. So this is, let's call it just generally condensation. So this is your velocity in that space times fi, so dmi dt, and it's equal to other processes that can change this particular beam here. So it can, unlike in space, where everything is kind of transported continuously through space, here you can have jumps, because if, for example, two particles here, this and that one, collide, they create bigger particles, so some mass is instantly in one time step added to this beam and subtracted from those beams. And that's a process called coagulation. General kind of term is like coagulation. And so we have some rate of change of this particular beam due to coagulation. And then, for example, in case of rain, if these beams, for very large beams, if they reach this kind of, like you say, your particles, actually this tail become bigger and bigger because this particles collision and producing rain. And rain can become so big, the rain drops become so big that they cannot sustain their spherical shape, and they start kind of breaking up into smaller rain particles. And you also need to take that into account. So this can be like break up. So break. And it could be another process. So somehow you need to initiate these particles, right? So some of these beams, small ones for small masses, should be the mass in them should be created by, for example, aerosol particles soaking in some water and becoming cloud droplets, and they now need to be added to that. Or some liquid particles can be frozen and then it become ice particles, and so they should be removed from your liquid water distribution and added to ice distribution. So this is a general term for that. It's some nucleation. So your I beam can change over time step due to nucleation or creation of new particles. So generally, so you understand that. Imagine like if you have like 200, usually like 100 beams is probably minimum. Particles in clouds, liquid particles, for example, the radius of cloud droplets and rain spans the range from like 1 micrometer, this is one of those smallest cloud particles that can be considered to be cloud particle, to something like in the order of 1 centimeter. At 1 centimeter is 10 to the 4th power, it's 10 millimeters, so it's 10 to the 4th power of microns. So 1 micron is 10 to the minus 6 meter. So you see, this is 4 orders of magnitude you need to cover in terms of size. With mass is of course smaller because it's kind of that's why it's beneficial to use mass variable, because you would kind of more uniformly cover this range using mass variable. But still you need at least probably 100, in the order of 100 beams to really resolve only these warm microphysics processes. And now, so you have 100 equations like that to solve. So for each of those beams needs to be transported in 3-dimensional space. And then for each of those beams you need to also transport them in size. So you mean how is them transport? They fixed, right? Well, yes, they fixed, but that's the thing. It's like grid. Like when in space, like if you have X, you have some distribution, concentration of something, and grid is fixed, but you need to transport it, right? So it's the same thing. So you transport it, and so you use some kind of scheme that computes this advection in mass space. So one of the most so now how you compute this guy? Well, this depends on your kind of model that you chose. For example, it is well known that condensation process for cloud droplets, so dr dt, the rate of change of cloud droplets, subjected to some supersaturation, so it's excess over 100% relative humidity, is so some coefficient alpha, which is a function of temperature and some other things. So we assume that alpha is known, but the main thing, it's inversely proportional to size of cloud droplet. So when size becomes bigger, the rate of growth actually slows down. That's why you cannot actually produce rain by this process. It's along, by condensation alone, because it would be too long time, because to grow 4 orders of magnitude in size from 1 micron to 1 centimeter size, let's say, it's actually would take you probably many days. And while we know that thunderstorms generate rain very, very quickly, it's because they mainly generate rain not by condensation, but by this collision of droplets with each other. But droplets actually grow. Initial stage is very important process of this condensation, but it's inversely proportional to radius. And mass is proportional to radius cube, at least this is for liquid droplets. For ice crystals, it can be actually not true, because for ice crystals, for example, if you have some plate, it may actually grow in size, in radius, but barely grow in thickness. So you have the mass proportional to radius square, or maybe something in between of those, because you have very large diversity of particles. So generally, you just assumes that there is some model. So for given cloud type, particle type, if it's a liquid particle like droplet, or if it's crystal, that you can generally write it as some a times radius in some power b, or even better, just that radius equal to a, no, not radius, let's write it that mass equal to a r in some power b, where b can be like some number from about 2 maybe to 3. In the extreme case of spheres, it's 3. If it's plate, it's 2, and something in between for ice crystals is pretty common. So if you substitute into this, you will have some another law, like for example, if you take differential of that, you have some a b r b minus 1 dr, so that your dm dt becomes a b r b minus 1 dr dt. And in this case, like for example, if it's inversely proportional to radius, then it's some formula, some, I don't know, some alpha prime, some coefficient, and here you have r b minus 2, something like that. And now you substitute that actually r is some 1 over a m to the power of 1 over b, so it becomes something like that, times mass. So you have some, but anyway, so you have this law that dm dt is proportional to some, again, some power law, that it's mass in some power b, well, different b than here, just, or let's call it alpha, here is gamma. So, but the bottom line that you actually can use pretty good, you have pretty good idea what your mass speed in the mass space depends on the mass itself, and the mass itself is actually mass of this particular being. So you know these velocities. You don't need to predict them. Each being has very particular velocity, except I didn't write here that here there is this Q minus Q saturation. So this is basically relative humidity excess. So it's relative humidity minus 100%. Well, or because we cannot use fractions, well, I mean percentage like minus 1. So when relative humidity is greater than 1 or greater than 100% is growth. So of course here you need to also add that relative humidity minus 1. So you have different velocities depending on relative humidity, but this part is actually known for each bean a priori. So these velocities are given. You don't need to compute them, kind of prognose them. You can compute them based on the field of relative humidity and based on the size of this particular bean. So this is in a way it's a simpler problem. Now if you start using, what scheme you would use here? You could use, of course, one of those positive definite advection schemes. That's one approach. Another popular approach, which is kind of in a way is more precise, is using Lagrangian scheme. So why Lagrangian? Because it's simpler, right? When if you watched my my lecture on semi-Lagrangian transport, in one dimension, semi-Lagrangian transport is very simple and efficient. You can run at very large current number. So you can use your Lagrangian scheme instead, but then you have this problem how to, for example, if you move to your spectrum using Lagrangian, here you can use just pure Lagrangian actually, because it's just one dimension. You move the whole probability distribution and then you recompute it back into the existing beans. And of course this process itself can represent some artificial broadening of the spectrum. And artificial broadening of the spectrum is a very bad thing for bean microphysics, because indeed these kind of spectrum outliers, these kind of guys, they're actually responsible mostly for initiation and development of rain. So if you artificially create them by these numerics in your scheme, you will produce rain much earlier, and then it's needed, or maybe it could be some other effects. So that's why it's very important how you treat this term. And many people in some models, I ask people like how they implement it. Sometimes I ask those people who do bean microphysics how they treat this condensation process, for example, and sometimes I get very kind of strange responses that, for example, they preserve only two moments of distribution, like mass and concentration. They think that it's sufficient. Actually, it's not sufficient in my opinion, and actually I've shown that in one of my papers when I was a student back a long time ago, that it actually can produce very wrong results compared if you, for example, conserve 4 moments of distribution instead of 2 moments of distribution. So you have to be extremely accurate how you treat advection in the mass space or size space using bean microphysics. Another problem is how you treat coagulation, and that's for that you need to solve so-called kinetic or coagulation equation, which is basically just a very simple idea. You can put like a mass as such way using logarithm that actually each bean can be produced, like if you collide 2 beans, you produce some other bean, and then this bean can be, so you need to keep track of beans that add to mass from collision of smaller beans, and then some process that actually removes mass from this bean by colliding of this bean with some other bean, which is actually larger in size than this bean, and so as a result it will be actually even bigger bean. So that's actually most difficult part of this code that you could actually encounter. And then also what is not known in this case well enough is what's the probability of creating, or when the 2 particles of certain sizes like this bean and this bean collide, what's the probability of producing this bean, because not all collisions end up by producing some new bean. Some collisions can be like elastic, so they just basically collide and then just go away without actually merging, so there is no coalescence process happening. So what you need to know here is so-called collision kernel. So this kernel, it's very, there are laboratory measurements of those kernels. They're just basically under, I don't know, microscope, collide particles of very small particles and see what the kind of probability of them merging or colliding. And also, in order for them to collide, you need to know their terminal velocity quite well. So, and that's for very small particles, you can use Stokes' law. For very tiny particles, for bigger particles, usually you use some kind of laboratory measurements. But those are pretty established, I would say. People also use numerical simulations of falling spheres through air. So I would say that terminal velocity of cloud particles are pretty well known, which is not known as so-called turbulence collision kernel. So there is this current research that demonstrates that actually a large portion of rain is created not just by colliding particles of different sizes, because they fall at different velocities and collide this way, but also they collide in this kind of as a result of dissipation of turbulence in air. So when turbulence through this process of cascading from bigger eddies to smaller eddies, they create this kind of regions of very intense turbulence, intense vorticity, and it's kind of like they rotate in very large speeds, and so by inertial forces they actually collide with each other. By that, even particles of the same size can collide this way. And so this coagulation kernel can explain this very early rain formation in certain clouds that this normal kind of gravitational collision theory cannot explain. So, but those collision kernels you need to basically tabulate. They usually can be modeled as some lookup table, and then so this is your most difficult part of the whole beam model, is this coagulation collision kernel. The computations, how they collide. And breakup is much easier. It just if you have certain size, you just basically put it distributed. You assume some probability of generating droplets of various sizes, so you put it back. So in general, for liquid clouds, this method is very robust and very theoretically and both observationally constrained. The problem that cloud physics has is with ice, and so with ice particles, it's not that easy. If they're not like you have one droplet collided with another droplet and created yet with just one also spherical droplet which is just bigger. With ice particles, definitely not the case. If you have one crystal colliding with another crystal, they're just two crystals stuck together. So how you describe it in terms of distribution function? So is it just a combined mass? And when these two particles kind of merge together, collide with third particles, they can break up very easily. And all sort of processes going on that very difficult to model, because you don't really know what's going to happen. Then you don't know what the nucleation process of your ice particles, because you don't generally know the concentration of ice producing aerosol in the air in this particular point in space. So beam microphysics, I would say, is great for liquid water clouds and those clouds are generally low-level clouds. All tall clouds, they always contain ice in them. So this method is really well developed only for warm clouds. So summarizing beam approach, it's very comprehensive, it's very interesting. It allows you to study effects of various processes on cloud size distribution and rain initiation process in clouds. It allows you to consider in great detail how aerosol, for example, is incorporated in clouds, how it's processed by clouds, and so on. But it comes with very heavy price of very large computational expense, because you have this extra dimension that you need to handle, and also you need to use very expensive and accurate advection algorithm to handle all this movement, both in a size space and also in just a geometric space. So So that explains why beam microphysics approach is very rare. There are just very few models that actually good models in terms of that have this beam microphysics approach in them. And again, beam microphysics itself is not better than other approaches if you're very sloppy about your numerics. If you're very not careful about this kind of issues, I won't believe your results, because I know that you can produce completely different results than other more also beam microphysics models using the same distribution of aerosol, everything. Your results will be drastically different. And that's because you're not so much careful about numerics. So it's very challenging area. And of course, fortunately for us, we don't have to do all this if we're not really interested in details of what's going on in clouds, but we basically treat clouds as something that provide two things. Latent heating due to condensation, flux of rain to the surface or to evaporate, and some measure of brightness of clouds in a solar part of the spectrum, and also some measure of the greenhouse effect. And that's basically most models need to successfully produce pretty accurate forecasts. You don't really need all these tiny details overall when you talk about large ensembles, because uncertainty due to turbulence itself and uncertainty due to dynamics can be much more important and more overwhelming than these differences in cloud microphysics among clouds, in my opinion. So there is another approach which is simpler one, completely different one. It's a bulk microphysics approach. As I mentioned before, bulk microphysics is basically, instead of predicting the full PDF of or size distribution of cloud particles, you predict only more moments of that distribution, like here, this concentration, let's say, or mass, or average radius and stuff like that. So how you do that? Well, you basically start from choosing a shape of that PDF. So you can use a prescribed analytical function for this PDF, like for example, exponential distribution, like also known in our field as Marshall-Palmer distribution of sizes, or some gamma distribution and stuff like that, or some other distribution that you want. The advantage of that approach that you can actually directly compute after you found your moments. You can actually find parameters of that distribution that you prescribe using those only several moments of that distribution. So, for example, so let's say that you have this analytical expression for your size distribution, or gamma distribution or whatever, and then you basically can then analytically or find some of those quantities that you're looking for example, sedimentation rate or creation of new particles and so on, just by modifying those moments of distribution, and then you find your parameters of your distribution from those few moments. Like, for example, sedimentation velocity. So in your equations, you have these terms like flux of this f of the distribution function due to sedimentation. So it's terminal velocity, which is a function of mass, times this f or PDF, also function of mass. So now you find the equation for your moments by integrating your prognostic equation for f that I wrote before. And if you integrate it, like say you're looking for moment m, like for moment some, let's say call it, let's call it m. mb. So it's such moment that it's integral from 0 to infinity of m in the power of b times f of m dm. So this is your moment b. So you take your equation for your moment b, and this, for example, this flux, sedimentation flux due to terminal velocity vt, and you multiply it by m in power of b, and now you integrate it. So this is your kind of sedimentation of your moment mb. Now by itself it's kind of useless. So what you do, you actually make it the following, as it's equal to some mean terminal velocity of moment mb times mb. And from that you see that this is actually equals to this your integral from 0 to infinity of mb vt, the function of m, f of m dm. And remember, fm is known to you, it's an analytical expression. So you need to be able, this f is chosen such that you can actually analytically integrate this, take this integral. If you cannot do it analytically, then it's pretty useless. You cannot do anything. You cannot take it, well, you can take it numerically, but it would be way, way too expensive. So it's easier to just to take it analytically. And now you divide it by mb, which is integral mb times in power of b f of m dm, and you multiply it by the same. So you didn't change anything. So this is your mb, and this is also your mb. So this whole thing is like, you know, it's like mb weighted. So it's weighted terminal velocity. So it's kind of average. Like, for example, if b equal to 1, then it's just mass, terminal velocity of mass divided by mass. So this is kind of mass weighted terminal velocity, or average terminal velocity of these particles of various mass falling down, distributed according to this prescribed function f. So this is how you find this. If you know analytical expression for f, this is how you find your terminal velocity given. So it will be some function, some depend. So this vt of mb will be some function of mb, and maybe some other moments, mb and other moments that you predict. So you know it if you know your moments, and times mb. So it becomes just normal advection term. And so on. There is no, in both microphysics generally, you don't predict supersaturation. Usually you assume so-called all or nothing approach, especially for liquid phase, because liquid clouds, they don't allow relative humidity in them exceed 100% by more than, say, 1%. So you, for practical reasons, purposes, you can say that it's exactly 100%. And then you can use so-called all or nothing approach by saying that all vapor above 100% relative humidity instantaneously condenses or goes into this certain, say, liquid phase or into the cloud water. And in the homework number 1 actually has such an example when you could find, using Newton's method, you can actually find cloud water from during condensation in an air parcel which is lifted and cooled while it's going up. This is exactly the problem when you use your nonlinear equation solving skills. So this is all or nothing approach. So there is no this movement of F in the space of sizes. You just instantly obtain condensate, total condensate, and you can do similar things to update your other moments using some parameterization assumptions. One of the most popular, so there are several popular distributions that people use for this bulk microphysics scheme. For example, first of all, different phases have drastically different properties from point of view of cloud physics. Like, for example, cloud water is predominantly grown by condensation or deposition or by evaporation. So those are main processes that affect those kind of tiny particles, like pristine ice. So you have cloud water, which is grown predominantly by condensation, and then you have so-called pristine ice, which is also grows predominantly by deposition or sublimation. And so those are what make kind of visible cloud, these particles. They're very tiny particles, and because they're very tiny, they interact very heavily with solar radiation. As a result, they're very visible. That's what basically makes visible cloud. But then you separately compute rain water or snow. Rainwater, or it can be snow, it can be hail, can be graupel, etc. And you predict separately, say, mass for those, total mass of those particles, or you can also add, and in that case, if you only predict mass, this microphysics, bulk microphysics scheme is called one moment microphysics or single moment microphysics. And of course, it's not very realistic, although it's very simple, but it's not very realistic because if you know only mass and you don't know concentration of those particles, then you have no idea about average size of those particles. And if you don't know several average size, you don't have no idea how fast they fall, because particles of various sizes fall very differently. And the difference can be from millimeters per second for cloud droplets to something like meters per second in case of rain. So you really need to know, and if you have the same mass, but it's tiny particles like drizzle, they will fall much slower, like maybe less than, half meter per second, while rain with the same mass, total mass, will fall much faster. So if you don't have any idea about concentration, you kind of a little bit iffy here. In case of cloud water and pristine ice, it's not that crucial because those particles inherently fall very slowly. So again, I mentioned that cloud water falls probably millimeters per second. And in that case, well, compared to all the strong updrafts, downdrafts of air motion and turbulence, maybe you can actually ignore that terminal velocity of cloud water. And similar thing for pristine ice, even although for pristine ice is a little bit less consistent with our knowledge of cloud physics, because even pristine ice, the particles are relatively large, so in the order maybe 100 microns, even like this tiniest, plates or dendrites. They're still large enough to fall appreciably fast, maybe tens of centimeters per second. So maybe in case of pristine ice, you can actually incorporate terminal velocity, but they all kind of fall with about the same speed. And that makes it even in pristine ice kind of easy also to sediment. And you just can assume that maybe your terminal velocity is some weak function of total mass. For cloud water, you can ignore sedimentation altogether. You say that it doesn't fall. So now you see you have the separation into small particles and large particles. And this separation, of course, does not exist in bin microphysics. There is no such separation. There is this continuous spectrum of sizes of particles. And in bulk microphysics, you always assume this kind of separation to various hydrometeors, so different types of particles. And rain is different than cloud water because rain is growing not by condensation. You can basically ignore that, but it grows by collision of cloud droplets with each other, and also by collection of or collision coalescence process, or collection of these rain particles, these cloud particles, when they fall through the cloud. So those two processes, so this is what mostly grows rain, and that's why it should be treated separately from cloud water in this approach. And also rain, of course, can evaporate. You can ignore condensation, but you cannot ignore evaporation outside of the cloud, because outside of the cloud, relative humidity can be considerably less than saturation vapor pressure. So it can be like 90% relative humidity or 80% relative humidity. So you need to account for evaporation. And for that, you also need to know size. So for rain, you need to know concentration in order to make more precise calculations of rain sedimentation rate and also evaporation rate, and same goes with two other large particles. So generally speaking, you need to know not only mass or first moment in mass space of particles, but also zero moment, which is concentration. But of course, it adds some expense and some larger uncertainty, because you need to also then have sources and sinks for each of those particles. So, for example, the process of creation of rain from cloud water is called autoconversion. And autoconversion is basically creation of large particles from collision of small particles. Even though such process as autoconversion does not really exist or precisely cannot be separated from other process, which is accretion or collection of rain particles of cloud particles or smaller particles. This is in continuous approach. It's all the same process of coagulation, just collision among particles of various sizes. But in bulk microphysics scheme, we need to separate them, because in the beginning, when we don't have rain, we have only cloud water. So we need some process that creates first initial rain, and this is what autoconversion does. And autoconversion rate can be modeled in many ways. Ad hoc wave, one of the first ad hoc ways to autoconversion is just to say that the rate of rain creation, say this is mass of rain, equals to some coefficient alpha, which you prescribed ad hoc from just, I don't know, typical value is like 10 to the minus 3 second inverse seconds times mass of cloud water minus some threshold cloud water, which you prescribe. So this one is typically something like 10 to the minus 3 kilogram of H2O of cloud water to kilogram of air. So this is mixing ratio. So and you multiply it by this kind of H of MC and MCO when MC is smaller than MCO, this H equal to 0, and when MC greater than MCO is equal to 1. So you have this kind of threshold cloud water after which rain initiation starts. So this process basically mimics or try to model this process when you have this kind of small clouds, relatively small clouds, fair weather cumulus clouds, when there is no rain from them. It's because they don't have enough of mass to produce one. So this is basically a very simple approach. This is called Kessler formula, and it's been invented by Kessler back in the 50s. Kessler parameterization. There are other more elaborate approaches to that that take into account the fact that it all depends also on the size of particles, how efficiently you produce rain. So if you have more like bigger particles in cloud, you produce more rain than you have all tiny particles, and for that you need actually second moment or concentration to get some idea about this process. So there is another parameterizations like that use both mass of cloud and also concentration of cloud particles, something like that dmr dt equals some coefficient A times mass of cloud in some power of B and times concentration of C, so concentration of cloud droplets in some power C. I when I was a student, I designed one of those schemes myself, and it's for some reason it became very popular, one of the most used in many models for some reason that I still don't understand, because I specifically designed it for a particular model and for particular cases, but people use this formula everywhere these days. And there are other people who design similar expressions using actually beam microphysics model. So I designed this and obtained these coefficients A, B, and C using beam microphysics model and basically estimate an autoconversion rate directly from the model for this beam model, and then produce this kind of parameterization for this rate of rain growth. Another process that rain actually can grow is from collecting cloud water. This process is called collision coalescence, and you can also model it by so-called continuous collection, when you basically compute total area of these shafts that rain particles fall through, and then if you know distribution of rain particle by size, for example, you can actually then compute how many droplets these falling particles sweep, and that's how fast this rain grows. And you can eventually also arrive to similar expression to autoconversion, but it's based that it also depends this mass of rain dt equals to A times mass of cloud water in some power B times mass of rain itself in some power C. So something like that. So you can actually find these coefficients from actually assuming this particular distribution functions both for cloud water and for rain. And here you can even maybe so it doesn't really it also can be times maybe your concentration of rain, if you have one, in some power of D. You can add that process too if you want. But the point is that you can actually derive this kind of parameterization, and that's what all differences among bulk microphysics schemes are all about. Is just people propose various ways to compute this kind of various processes. And in case of ice microphysics, there is also a similar process to autoconversion that actually creates snow. So there is some snow created from pristine ice using some thresholds as well, for example. Or hail. Hail can be also produced from pristine ice as an autoconversion, or freezing rain can, so rain particles, if they get very at the levels where it's very cold, you can move them to the hail category, and then this hail can fall through pristine ice or through supercooled cloud water, which always exists in freezing temperature. Cloud water does not really freeze until it's minus 40 degrees Celsius for practical by itself, or with the aid of some ice nuclei can freeze a little bit earlier. But overall, there is always cloud water, liquid water at not very cold clouds, again warmer than minus 40 degrees Celsius, and this water is collected by hail, and hail can grow by that. And you also use formulas similar to that for this process. And also there is this kind of freezing of cloud water to produce pristine ice as well, and vice versa. When pristine ice gets below zero level, so below 0 degrees Celsius, warmer temperatures, it melts and produces cloud water, for example, or it can produce rain or drizzle if you introduce such category, additional one. So all cloud microphysics has this kind of spaghetti diagrams when they have all this kind of categories of cloud material or hydrometeors connected with all these arrows through various processes, and then they describe each of those arrows as some formula. And then you basically, that's what makes one microphysics scheme different from another one, how you actually draw these arrows and which formulas you use. So I'm not going to talk about specific microphysics, but many of them use two main distribution functions. I just finish the lecture with mentioning those. So the most probably for so-called single moment microphysics, remember that the one that predicts only mass, the most common one which is used is so-called Marshall-Palmer distribution. So it said that this f as a function, say, or diameter of particle, or radius of particle, regardless, or mass, if you can convert it always. For in case of liquid phase, it's very easy to do, to convert from mass to radius, is equal to some n naught e to the power of minus lambda d. So this is exponential distribution. So it looks something like that. So this is d, this is f. So it's something like that. Or actually not. It's not like that. It's so when d equal to 0, this one is equal to n naught, and then it just goes like that. Well, like that. So in that case, the most important aspect why it's called Marshall-Palmer, not just exponential distribution, that they back in a long time ago in 50s, they did this experiment when they actually measured this distribution of rain falling at their kind of I think it's the like pieces of filter paper or something. When a droplet actually gets into it, it makes this kind of impression on it, and then they basically collected many of those and then just measured it by hands, the size of this droplet distribution, and they plotted it. So if you plotted it as like you take a log, say of d, in that case no, a log, not d, a log of f. So you take, then it's going to be linear function. So it would be something like that. And they measured from various cases for various rain rates. And they noticed this interesting thing. These all distributions intercepted in about the same n naught. So this is kind of interesting that from the experiment, this n naught was equals to 8 to the power of 6 meters to minus 4. And so you basically then know this n naught for rain. But again, this one is all only collected for specific type of clouds, really in mid-latitude. So it's not necessarily that this n naught is the same in tropical clouds, although it's awfully close. So this is basically the basis for using Marshall-Palmer distribution, because you just basically specify your n naught. And now lambda can be found for specific moments that you have, from the total moment if you know n naught. First of all, you know concentration. You can obtain concentration by just taking this distribution and integrate it by concentration and integrated at f of d dd, and this produces your concentration. I'm not going to write it, but you can actually, as a function of some lambda and n naught. Now you have first moment. You predict first moment only in this using this Marshall-Palmer distribution. You don't need concentration anymore, because you can actually compute it, because you already prescribed your n naught. So you know concentration. And you know concentration, in fact, from mass. If you integrate using a third moment, which is mass, a third moment for is a function of d, then you can actually compute that this, I'm not going to do it, but you can do it yourself easily, that lambda equals to pi n naught raw water, density of water, then density of air, times this mass of rain, or mixing ratio, in the power of 1/4, the 1/4. So if you know mass and everything is given, you know density of water, you know density of air, you know n naught, because you prescribed it to this number, you know pi, and you know lambda, so you know your whole distribution. And from that you can compute mean terminal velocity according to that formula that I gave you. You can compute collision with cloud with cloud water, for example, assuming because different particles of different size, rain particles of different size, will collect different amount of cloud water because they have different different sweeping kind of volume. So you can find you can easily compute those things if you assume this Marshall-Palmer distribution. So basically, and you use autoconversion to initiate this, some formula for autoconversion to initiate this MR, and then it's evolved, this MR is involved by due to advection around your field, and also due to the sedimentation process and collection process and other processes, and evaporation. You can compute evaporation rate given MR as well, evaporation outside the cloud. So all those very, I don't want to provide you details because they kind of, well, you can, they're not complicated. You can find it in any kind of article that describe any microphysics that assumes Marshall-Palmer distribution. So, and again, you can use it because you can specify n naught. Another approach, and similar approach actually has been used for ice, for snow, for example, for graupel. They also specify some n naught, but using some maybe observations, and n naught for snow and for graupel is different than for rain. So you just use different value, like for example, somewhere here, this is your distribution for snow. And you have different n naught for snow. And then you can use single moment microphysics, because you don't need moment, for example, for cloud water. You can actually assume, because it doesn't sediment, you can use all or nothing approach to condensation, so you don't need concentration because, well, you don't need it. You just condense everything into mass, all excess of water vapor into mass. So usually single or double moment distribution is used mostly for precipitating particles to basically, because that allows you to compute different sedimentation rates and so on. So single moment microphysics all rely basically on Marshall-Palmer distribution. But double moment microphysics, so when you use two moments, like say mass and concentration as separate variables, then you actually need some other distribution to assume. And usually people assume a so-called gamma distribution. Yeah, a gamma distribution which is the following. And why they use gamma distribution? Because it's very easy analytically to compute various moments of gamma distribution just analytically. That's why people like gamma distribution. It looks like the following. So it looks like it's kind of skewed. Maybe not like that, not like bell shape, but like that. So this is gamma distribution. And generally written as like f of radius, function of radius, equals to n r in power of gamma divided by gamma function of gamma plus 1. And you know what gamma function for integer gamma is just factorial. So gamma of n plus 1 equals to n factorial. But for things like on computer, you can easily compute this function. It's one of the intrinsic functions that are provided with your compile language. So this is easy function to compute. Times beta, the power of gamma plus 1, e to the power minus r over beta. Where beta and gamma are two parameters of gamma distribution. Usually gamma is fixed. In that case, it's two-moment microphysics, 2 moments only required to compute everything. So first of all, you need concentration. This is right away. N is concentration. So you already have concentration here. And also, you can always compute beta from mass, say, of rain and concentration of rain. So here is concentration, say, of rain. You can find beta, and gamma is usually fixed. And this one also used not only for rain, it can be used for cloud water. In that case, it's actually more appropriate even to use for cloud water, because for rain, for rain you can use Marshall-Palmer, but if you want to be more specific about cloud water, you're interested in kind of in size of cloud particles for your, say, radiation computations more precisely, then you use, of course, gamma distribution. And gamma usually fixed. Something like gamma can be like from 2 to 6, usual kind of choice. Or it can be computed. In that case, you need 3 moments of distribution. You need mass, you need concentration, and also, for example, mean radius. And if you can separately prognose it, I developed models like that when I was a student for my PhD dissertation that actually predicted 3 moments of this distribution using gamma distributions. And it was surprisingly produced very close results to prediction of much more sophisticated bin microphysics. So just using 3 variables instead of hundreds variables, it produced virtually identical results, very similar results. So that's because for this case, gamma distribution is really closely approximate observed distribution of cloud particles in certain type of clouds. So that's basically the idea. You use gamma distribution, and then you find all the moments, interaction with them. Or you use, if you use single moment microphysics, you use Palmer distribution, Marshall-Palmer distribution. So that's basically it. That's basically all I have to say about ball microphysics.